Hey, yeah, so thank you everyone for coming. This is our third session of the um, Bilevel optimization webinar. And today we have Miguel from Edinburgh um, talking about the computational complexity of unboundedness in Bilevel optimization. And Miguel holds a chair of operational research at the School of Mathematics, University of Edinburgh. And he previously held a faculty position at Polytech Montreal, at the University of Waterloo, and the University of Southampton. He's the founding academic director of the Trout Institute of Energy at Polytech Montreal. His, his accolades include an India International Chair, a Canadian Research Chair, the NSAC Hydro-Quebec Schneider Electric Industrial Research Chair, Queen Elizabeth II Diamond Lee Medal. He's a fellow of the Academy of the Mathematical Society, Science of Europe, and the Canadian Academy of Engineering. His research interests are in mathematical optimization and its industrial applications. He has published 4 books and more than 100 scientific journal articles, and has led research collaborations with companies such as EDF, Hydro-Quebec, National Grid ESO, currently known as NESO, Rio Tinto, and Schneider Electric. Professor Anjos serves on the board of the Oral Society and the chairs of the Society's Research Committee. He's previously served as a chair of the Mathematical Optimization Society, Inform's vice president for international activities, and the president of Inform's section of energy, natural resource, and the environment. Thank you for accepting our invitation, Miguel. And without further ado, the floor is yours.
Thank you, Nagisa, and thank you indeed to the organizers of this series of webinars for getting it off the ground and really keeping the community together through this way. I think it's an excellent initiative, and good to see the Bilevel Optimization Society having regular activities and keeping people connected in this way. I appreciate the opportunity to present here. It's really a pleasure, and what I want to present today is some work that I recently completed with some other people on the question of unboundedness in bilevel optimization, and I'll give you a little bit of a question motivation for why we started looking at this question and some of the results that we got so far about this. Whoops, let's see, there we go. I want to start by saying thank you to the fantastic people that I participated with in this work. Bárbara Rodrigues, who's a former PhD student in Edinburgh and is now an optimization analyst at Edinburgh Airport. Margarida Carvalho, who's a professor at the University of Montreal. And Nagisa Sugishita, who is here today and just is one of the organizers of this series. So it's very nice to be presenting some of the work that we did together here as well. And if you want all the details, the paper has just been published a few weeks ago in Mathematical Programming, and I've put the DOI link here on the PDF. I'll start hopefully at a point where everyone is familiar with what this is in this group at least. We're going to be talking about linear bilevel optimization. So I'm looking at the problem of minimizing a linear function of two variables, x and y tilde. And the set of feasible pairs xy tilde is going to be denoted F sub BL, so it's bilevel feasible set, or the inducible region that is often called as well. I have this minimization subject to some linear constraints on the x and the y tilde, and the y tilde is an optimal solution of this lower level optimization set, where I'm minimizing f transpose y, so a function of y here, and then some constraints with respect to x and y as well. So y tilde denotes an optimal solution of this problem that is a problem in y. And the point is to make a distinction between the variable of this lower level and the optimal solution that is then used at the upper level. And this matrix B, that's the coefficient of y tilde at the upper level, is if it is equal to 0, that means that we don't have coupling or linking constraints. And if it's not 0, then we do have coupling or linking constraints. And some of the results that we have some assumption on what happens with respect to the linking constraints. I assume this is pretty much known to everybody here. And what we now want to ask is a question of, if I'm given a linear bilevel optimization problem of this form, how can we determine if it's unbounded or not? Now, what we mean by this, again, more specifically, is that if we take the bilevel problem and just ignore this line here of the lower level optimization, we have a set of linear constraints by putting these two together. And if I do that, then I get what's typically called the high point relaxation. And the idea now is going to be x is the upper level variable. I pick a value of x, and then the possible y's are the ones inside the high point relaxation for that value of x. And then because the lower level is optimizing in this direction, we will pick the lowest possible y for that x. And this green area, this green set, which is, as you can see, a combination, a union of two lines, or line segments in this case. This is the feasible set of the bilevel problem. And now the upper level optimizes in this direction. So assuming that the set stops here, this would be the optimal solution for the bilevel problem, because it optimizes the upper level with respect to the green area. If the problem is unbounded, then possibly this green segment would continue off to infinity, and we could keep improving the upper level, and therefore we would have an unbounded problem. So that's what the question is can we find such a direction of unboundedness for the bilevel problem? And more specifically, what we want to know is, can we find a feasible solution, x bar, y bar, and a direction of unboundedness, delta x, delta y, so that starting at x bar, y bar, I can take an arbitrary large step in the direction delta x, delta y, and I remain bilevel feasible. And I have if I plug the direction delta x, delta y in the objective function of the upper level, then I get a negative number, which means that my upper level objective keeps improving as I move in this direction. And then I can continue indefinitely improving the objective function without any limit. So that's what it means to be unbounded. There's, again, in the picture here, this would be my x bar, y bar, and this would be the direction of unboundedness. So the question is, given a linear bilevel problem, is there such a pair x bar, y bar and a direction delta x, delta y to show that the problem is unbounded? The motivation for asking this question is that if one looks at the literature on bilevel optimization, most algorithms, certainly for solving bilevel problems, start by solving a single level linear relaxation, typically something like the high point relaxation. And if you look at the algorithm and the theory behind the algorithm, it's regularly assumed that we're dealing with a bounded set. So we're having a bounded HPR, and if we have a bounded HPR, clearly the green set, the bilevel feasible set, will also be bounded, and so we're fine. But the question is, what if the HPR is unbounded? Well, if the HPR is unbounded, then we have no idea, because everything can happen. We can have a bilevel problem that is finite optimal, that is infeasible, or that it's unbounded. So if the HPR is unbounded, we have no guarantee about what's going to happen, and we have to investigate further. So basically the question is, if the HPR is unbounded, how can we check that the bilevel is unbounded? But first, we also ask the question, how difficult is it from a complexity point of view to check whether the bilevel problem is unbounded? Because we know that in bilevel optimization, the difficulty of problems is often a relevant issue. So how difficult can it be to check unboundedness for the problem? There are some results in the literature related to this, but most of the work in the literature looks at unboundedness of the lower level problem. It's not the bilevel problem as a whole. So there's some results. There's a result that says, for example, that if there is a feasible upper level solution such that the lower level is unbounded, then the bilevel problem is infeasible. So this is one way of checking, of showing that it's infeasible, which means it's not unbounded. But that's what that result tells us. There's some other work that shows that when the HPR is unbounded, one can detect whether the lower level problem is unbounded by solving a linear problem, and hence determine if the bilevel is infeasible or if the lower level is well defined. So again, it's focusing on what happens at the lower level, but it doesn't really tell us, okay, the HPR is unbounded. What happens for the whole problem in terms of the bilevel problem? And then finally, there's this very nice algorithm here that's got a great name, which is the watermelon algorithm. And it looks essentially at the question that we're interested in. It looks at integer linear bilevel problems, and it can provide a certificate on unboundedness when one exists. The interesting thing that happens here is that this algorithm is for integer linear bilevel problems, and so one would think, well, we can just apply it to non-integer problems. But in fact, the algorithm depends on the integrality property because it uses a branch and bound with disjunctive cuts. So if we don't have the integer nature of the problem, we actually, I mean, it's not straightforward at all how to use this algorithm. So we do have an algorithm for the integer linear case, but not for the non-integer linear bilevel case, which is what we're interested in today. So as you can see, some authors have looked at this question before. There are some results known, but really the focus of our work was to say, okay, so let's look at the very basic question of what we call unbounded BLP, so bilevel programming. We have the data, the matrices A, B, C, D, the vectors A, B, C, D, F. We assume that they're rational. We assume they have the right dimensions. And then the question that we're asking, first of all, from a complexity theory perspective is this problem, is the corresponding bilevel problem unbounded? And what we've shown in the paper is that this decision problem, as I just stated it, is strongly NP complete. So it's both in NP and strongly NP hard. How we do that? Well, one of the things that we use is we use this reformulation as a finite union of polyhedra. So this is also a well-known result that we can take a linear bilevel optimization problem, as I stated at the beginning, and reformulate it as a finite union of polyhedra. So here I have the same objective function that I had for the original bilevel problem. I'm minimizing over x, y, and now lambda, which are going to be the dual variables. And I want these pairs x, y, lambda to be in the union of a certain collection of polyhedra, and these polyhedra are essentially defined by having the complementarity questions of between the constraints in the primal and the multipliers, the variables from the dual being equal to 0 or not. So this omega is a decision that says which of the two parts of the complementarity I want to fix to 0. And then the lambdas, as I said, are the feasible set of the dual of the lower level problem. One thing that I didn't specifically mention that's related to this is that if I come back to the very beginning here with the problem, a common approach to linear bilevel is to take the lower level problem and replace it with the optimality conditions, the KKT conditions. So we would have primal feasibility, which are these constraints, dual feasibility, which is the feasible set for lambdas, and complementarity between these constraints and the lambdas. And that is exactly what I have here. Okay, so these are the primal feasibility and this is dual feasibility for the lower level problem. So essentially what this is saying is, if you tell me, you know, if the problem can be reformulated so that it boils down to deciding which of the complementarity terms is equal to 0 in the KKTs of the lower level problem. And if I know that, then I can basically solve the problem because everything else is linear. And I have this union of polyhedra because I have multiple green pieces in my feasible set. So in general, the feasible set of a bilevel problem is a union of polyhedra of this form. This is important in our work in particular because we're going to be using this feasible set for the dual problem later when we talk about algorithms. So this set will show up again a little later in the talk. Now, first of all, let's look at inclusion in NP. So again, back to our basic unbounded bilevel decision problem. And the theorem is that the finite union of polyhedra reformulation is unbounded if and only if the original problem is unbounded, and if and only if there is a choice of these omegas, 1 or 2, so that this linear problem is unbounded. So is there a way to pick my complementarities so that the resulting problem, resulting linear optimization problem is unbounded? Okay, so really I'm just saying I can look at the finite union of polyhedra as a way to look at unboundedness of the original problem. And what this is useful here because it means that the original unbounded BLP problem can be expressed as, can I find a choice of these complementarities, these omegas 1, 2, so that the resulting linear problem here is unbounded. Okay, and this is now another decision problem. Is there such a choice of omega? Yes or no? Okay, and this is a formulation with a single existential quantifier, followed by a property that is checking whether a linear problem is unbounded, and this property can be checked in polynomial time. Using an algorithm by Yi, Todd, and Mizuno in 1994. So what this means is that this problem is in NP. If you give me the right choice of the complementarities set to 0, I can check in polynomial time that this is correct, that the problem is unbounded. Okay, so that shows that it's in NP. If we now look at the strong NP hardness part, what we do here is a reduction from 3-sat. So 3-sat is one of the original NP complete problems from the 1970s in the well-known 1979 book by Gary and Johnson, and it basically says I have a logical expression where every clause has 3 variables, and I have the end of every clause, and the clauses are ORs, and I want to check if this Boolean expression, this logic formula has a true or false assignment that will make it true. And what we have is a reduction from this problem to the unbounded BLP problem, which basically means that the unbounded problem is strongly NP complete. But important point here is that this proof depends on the fact that there are no coupling constraints. So if there are coupling constraints, this result doesn't hold. So basically, we have shown that unbounded BLP is strongly NP if I just come back here, is strongly NP complete, but part of the proof hinges on the fact that there are no coupling constraints. Now, before moving further, the next observation is that when we speak about bilevel optimization, one of the aspects that also comes up is this question of optimistic versus pessimistic. And this is an issue when the optimal solution to the lower level problem. So if I come back to the beginning, these y tildes here, if this y tilde is not unique, if there are multiple solutions that give me the same objective value for the optimal value for the lower level problem. In that case, we have to somehow answer the question, which solution do we pick? So which solution is assigned in that lower level constraint? Now, if the solution that is chosen is the one that most benefits the upper level, this means this is what we call the optimistic formulation. So the interpretation of the bilevel problem is that the y tilde is going to be the best possible y tilde for the upper level problem. The pessimistic formulation says that it's going to be the worst y tilde from the point of view of the upper level problem. And this has a bearing in our question about unboundedness, as I'm going to show you now. One of the things to observe here is that the optimistic formulation, so we choose the lower level optimal solution that is best for the upper level, can be written in this way. We have the objective of the upper level, and we have a minimization over the x variables of the upper level, and then a minimization over the y's, which are in the set of optimal solutions to the lower level. That's what this S of x says here. So you pick an x that is feasible for the upper level, and then we have a set of optimal solutions for the lower level, and we pick a y from that set that minimizes also this function. If we go to the pessimistic formulation, we have a min-max, because now the leader, the upper level, is minimizing, but the lower level will be picking the worst possible solution for the leader, so it's going to be a maximization on y of that objective function. So this is the pessimistic version. This is the optimistic version. This is the pessimistic version. And finally, we can also note that this pessimistic version can be written as a min-min if I add a constraint here that says that this objective function has to be at least the objective function with y tilde plugged in for all possible y tilde in S of x. So in particular, this has to be true for the worst y tilde in S of x, and therefore, even though I have a min here, it becomes equivalent to the pessimistic formulation. Okay. But the key point is that how you choose the y from the lower level determines whether we're looking at optimistic or pessimistic. Now, what happens here with unboundedness? Well, in general, one result is that the unboundedness of the optimistic formulation does not imply unboundedness of the pessimistic. And we have I have here an example to illustrate that. Here's a linear bilevel optimization problem. I have minimization on x at the upper level, and I've put it in quotes because this minimum is actually not well defined, but let's not worry about that for now. I'm minimizing minus x plus y1 plus minus y2, and y1 and y2 are optimal solutions to this lower level problem, which is the minimization of minus y1 minus y2, subject to minus x plus y1 plus y1 bar plus y2 bar less than or equal to 1, and the y1 and y2 bars should be non-negative. Okay, so this is my bilevel problem that I'm looking at. If we start here with the lower level constraints, given a fixed x, I can observe that this constraint restricts this feasible x to be at least minus 1, because if this x is less than minus 1, because these y's are non-negative, it's impossible to satisfy this constraint. This value here, I'll move it to the other side, and I end up with something that becomes negative, greater than or equal to 0, because these are bounded below by 0, and that's not feasible. So any feasible x is in fact restricted to -1 to plus infinity, so at least -1. Okay. Now, suppose that I have an x bar that's at least greater, that is greater than or equal to -1. Now, the set of lower level optimal solutions for the lower level for that x, so this S of x is equal to the pairs y1, y2, so that they satisfy this constraint, because I'm minimizing -y1 minus y2. So I'm going to always push against the constraint, and this is going to be equal, and y1 and y2 have to be non-negative. Okay, so this is the set of optimal solutions of the lower level for an x that is feasible in this set. So now the question is, what happens if I look at the upper level objective with this optimal set for the lower level? And what basically happens if I draw the picture here is that this is in y1, y2 space. So x is at least -1. If I fix an x, then I will get a line that is of exactly essentially a 45-degree angle, like a simplex line past the 90 degrees, and I have these two intersection points that are going to be 1 plus x bar on the y1 axis and also 1 plus x bar on the y2 axis. Because what's happening here is that I have this equality, and I pick each of the y's equal to 0 in turn to get the intercepts of the two axes in y1, y2 space. So the two intercepts are 1 plus x bar, 1 in y1, y in y2. And I have this nice simplex here. Now, all the points on this line are going to be optimal, because I'm really picking points on this line, which is the set of optimal solutions for the lower level. So all of these points are optimal for the lower level. And now the upper level objective is pointing in this direction, because it is minus x, which is now fixed, plus y1 minus y2. So it's exactly this direction here. And if I'm optimistic, I will pick the point on the green segment that is best for the upper level, which is this point here. If I'm pessimistic, I will pick the red point down here, because it's going to be the worst for the upper level. Okay, all of these points are optimal. This is the pessimistic solution. This is the optimistic solution. Sorry, the other way. This is the optimistic. This one is the pessimistic. What does this mean for unboundedness? Well, if I now plug this in, I get that for the upper level objective in the optimistic version, the objective value is now minus 2x minus 1. Remember that x is still a parameter here. All I know is that x is greater than or equal to minus 1. But whatever it is, this becomes the optimal value for the optimistic version for the upper level. And if I plug in the pessimistic solution, then I get a constant of 1 as the optimal value for the upper level. So in the optimistic case, I can find a direction of unboundedness. I can keep moving in the direction 1, 0, 1 for delta x and the delta y1, delta y2. And this allows me to make this minus 2x minus 1 as negative as I want. So it's unbounded. But in the pessimistic case, no matter what I do, the objective value is constant. So the problem is going to be bounded. So this is an example where the optimistic is unbounded, but the pessimistic is bounded. Now, if we go back to the theorem that I just mentioned before, the NP-hard part still holds if we consider the pessimistic formulation. So because the lower level optimal solutions in the reduction are uniquely defined by the upper level. So essentially the the reduction is equivalent and it still works. So I still have that in the pessimistic case, deciding whether the problem is unbounded is strongly NP-hard. That one carries through. Furthermore, we have a result from Zare in 2018 that shows that even if an optimistic or a pessimistic solution is known, finding a pessimistic or optimistic solution, so the other one, remains NP-hard for the same problem. And there's a natural question, which is whether knowledge of knowing the unboundedness of one formulation helps in determining the unboundedness of the other. And the result that we do have is that if the pessimistic is unbounded, then the corresponding optimistic will be unbounded. We know that the converse is not true. If the optimistic is unbounded, the pessimistic can be bounded, but if the pessimistic is unbounded, then we know that the optimistic is also unbounded. Okay. So this is the relationship between pessimistic and optimistic from an unbounded point of view. Right, now we can ask the same question and say, okay, we have seen that for the bilevel linear problem, we have a strongly NP-hard problem. What happens if I have more than two levels? This is also a natural generalization in well, bilevel or multi-level optimization in this case. So if I have a k-level optimization problem where I'm minimizing a linear function subject to linear constraints and then having an optimal solution to another linear problem, which itself has another linear problem as a constraint, and I do this k times. The main results that we have here are that we can look at unbounded KLP. So if I look at k-level linear programming, bilevel programming, k-level linear programming, is this going to be unbounded or not? That's the decision problem. And then what we've proved is that this problem with coupling constraints is sigma k minus 1 p hard. So if we have two levels, this would be sigma 1p hard, so NP hard, or strongly NP hard. And then if k is 3 or more, then we have sigma k minus 1p hard. And then if we now have a mixed integer version of this problem, the level of hardness is one higher, so it's going to be for the same k level optimization, the mixed integer version is going to be sigma kp hard as opposed to sigma k minus 1p hard for the non-mixed integer version. And again, this is expectable because as you add levels to the problem, the complexity should go up. So in summary, what we have in terms of complexity results is that we have results for the linear bilevel optimistic and pessimistic, and for the mixed integer bilevel optimistic and pessimistic in terms of the complexity of determining if these problems are unbounded. And for k-level, we have the complexity for the optimistic case. If anyone is interested in looking at the pessimistic case, at least as far as these results go, it's not yet known. So that's a question that remains undetermined here. But that's looking at complexity. Now, in the last few minutes, what I want to do is talk about algorithms. Given a linear bilevel optimization problem, what can I do to try to determine computationally if the problem is unbounded? Well, one approach is to say, let's look for that direction of unboundedness. So we can prove that the bilevel problem is unbounded if and only if this linear program with complementarity constraints, or LPCC, has a strictly negative optimal value. So the idea here is I want to get a descent direction, and if it can go on in that direction, I want to make sure that it's going to be unbounded. So what I do is that I want xy lambda, this triple, to be feasible for the high point relaxation and the dual set, a bit like a dual feasible set for the lower level as we did before. I have here my complementarities. We already talked about this. I want to remain feasible for the upper level and for the lower level. And I want to have complementarity on the direction delta x, delta y as well. So the first complementarity is for the point xy, and the second complementarity is for the descent direction, delta x, delta y as well. And I can put bounds on delta x, delta y, which is a kind of normalization, because I just need a direction. I can just do a normalization on delta x, delta y. And if what we can show is that if I find a feasible solution to this problem with a strictly negative objective value, this is going to be bounded, by the way, because I have these bounding constraints here. So if this optimal value is negative, then I have a point xy and a direction delta x, delta y that shows unboundedness of the linear bilevel problem. Okay. So I can solve this. The tricky part here is that this is a nonlinear problem because of the complementarity constraints. So everything is linear except the complementarity constraints. I can turn this into a mixed integer problem by using integer binary variables and big M type constraints. I can attack this with a nonlinear problem. Doesn't really matter how you do it. If you can find a solution to this problem that has a negative, strictly negative objective, then we've achieved the purpose of showing that the original problem is unbounded. There is another way of looking at the problem. Instead of turning these constraints into linear constraints or attacking with a nonlinear problem, it's to say the following. Let's remember the feasible set of the dual, the feasible set of the dual of the lower level problem, which is this set here. This set only depends on the lambdas, and it's a polyhedron. And therefore, what one can do in principle is to check all the vertices of this polyhedron in lambda. And for each vertex of this polyhedron, I have a fixed lambda because I'm fixing a point in this feasible set. And if I fix a lambda and come back here with these lambda fixed, everything is linear in this problem. So I can enumerate the vertices of this feasible set, and for each vertex I run an LP and I check if I get a solution to my unboundedness or not. The moment I find one, I'm done. Find one with an optimal value less than 0, then I'm done. I know the original problem is unbounded. Otherwise, I go to the next vertex and I solve the LP, check again. And if I run this for every vertex and I cannot find a value of lambda that gives me an unbounded certificate, then I know that the original problem has to be bounded. So this approach has the advantage that it's well defined. It's going to be finite, but it involves enumerating vertices, which is normally not an easy problem. It really depends on how many vertices you have in the polyhedron, and that can take quite a long time. And what we did is we did a computational comparison of these two approaches. We looked at instances from the Bilevel benchmark instance of benchmark library of instances for bilevel optimization. One of the issues is that all the instances in the benchmark library are bounded. So we cannot test our algorithm on any of them. What we had to do is relax the bounds on the decision variables to try to make the instances unbounded. And in this way, we were able to get 48 instances with an unbounded HPR. And now the question is, for each one of them, is the original bilevel problem bounded or unbounded? We ran both algorithms, the LPCC approach. So this is the nonlinear approach with the complementarities. This is the vertex enumeration algorithm. And the LPCC approach was able to resolve all the instances, the status of all the instances, and the running times were actually not bad at all. The longest time, this is average time overall the instances that fall into this category. So it basically, I think what it really tells us is that this algorithm for all these instances ran in very reasonable time, in half a minute, in less than half a minute, basically on average, and the infeasible ones were resolved very quickly, pretty much all the time. On the vertex enumeration side, some of the instances we were not able to resolve within, this was with 2 hours of CPU time. The ones that did resolve, the 9 instances here, took well over an hour of CPU time on average. These 11 instances still took quite a bit of time, but the infeasible instances for the vertex enumeration approach were also very quick to solve. I think, to me, the main conclusion from these results is that in general, for these instances, at least the LPCC approach seems to be more reliable in terms of being able to give a solution in reasonable time. But it's a very small test set. And there may well be instances, there may be specific cases of instances where a vertex enumeration approach could be superior, especially if there's structure that can be exploited here for speeding up the enumeration. So that's pretty much the main points from our paper. In terms of thoughts for future research, as I mentioned, there's still some cases of the complexity question that are not resolved. In particular, the mixed integer pessimistic case, and also we did K-level, but it's single follower at every step. So one question could also be, what happens if we have multi-follower problems? How does this affect the complexity? From the point of view of computation, I think there's definitely a need to carry out more extensive experiments to really get a better sense of the performance of the two approaches that we proposed. And I think in general, what I would like to just point out is that I think it's worth paying a bit more attention to account for unboundedness in computational approaches to bilevel and multilevel, because if the problem is unbounded and one hasn't realized it, then the algorithms can really have strange, unexpected behavior, because most of the time it is assumed that the problem is bounded. So I think it's something to keep always in mind when looking at solving bilevel problems. And on that, thank you very much, everyone, for attending and for your attention.